going? Yeah, cool. So this is on page 123. You've got this reaction here. 4HCl plus O2 makes 2HCl plus 2Cl2. Now we've got this thing here called the equilibrium constant. And it's Kc. It contains no units. So this is now a mathematical expression. This is something you need to just remember. If the Kc is greater than 1, then the products will be favoured over the reactants. So if that's greater than 1, then we're going to be making water and chlorine. If it's less than 1, then you'll favour the reactants over the products. So it'll be over this side. So it tells you mathematically where the equilibrium sits. And there's an expression method that you use. So if you've got, this is just made up, there's the molar coefficient and the chemical, molar coefficient chemical, equilibrium reaction, same and same over here. So when you work out the Kc, it's always products over reactants. Now what does the square brackets mean? No, good shot though. Concentration. Square brackets means concentration. Normally you might be used to seeing this, C of H to O equals X number of moles per litre. Water's probably a bad example. Concentration of HCl in water. But in the case here, we now represent it with square brackets. So this means concentration in moles per litre. That's the molar coefficient. So if that was a 2 there, you'd have a 2 here, so it'd be squared. If that was a 1, then you just have it to the power of 1, which is nothing. If it was a 3, it'd be a 3. So it's the same bouncing ball process every time. Now question 5a is write the expression for the equilibrium constant Kc of this reaction here. So remember we do products over reactants. So the product's going to be Cl2 and H2O with your brackets around it for the concentration over O2 and HCl. And it's not finished yet. Now we look at the coefficients. So in front of water and chlorine gas we've got 2's. And in front of the HCl there's a 4. And in front of the O2 there's nothing. So whatever the concentrations are for chlorine and water, we're going to square them and then they're times together. And that'll be the top. And then down here, whatever the concentration for the oxygen is and the hydrochloric acid, oxygen will be times by the hydrochloric acid, which has been put to the power of 4. And that will then work out your Kc value, and then you determine, is it greater than 1 or is it less than 1? And that'll tell you where the equilibrium is lying. And when you turn the page, well actually I'll read the question. The Deacon process is an industrial process that converts hydrogen chloride into chlorine. An experienced chemist can demonstrate the Deacon process in a sealed vessel using copper chloride catalyst. The demonstrator mixed 1 mole of hydrogen chloride with 0.25 moles of oxygen in a 5 litre vessel, which was heated to a constant temperature of 350 degrees. 0.5 moles of hydrogen chloride was present in a 5 litre vessel at equilibrium. Write the expression. Sorry? Someone said something. No? Right. Now we've done the expression, but when we turn over the page and it says complete the table below, so the red areas that are blanked out there, well that's what we call an ice table. So initial, change, and then your concentration. I've actually seen the question where you have to draw your own ice table and not fill it in. That was weird. Okay. And you need a row for each chemical species. And then up here you write the chemical species. So here, HCl. Here is O2. Here is H2O. and here's Cl2. Now I want to make a point here. This is for a reaction carried out at 350 degrees. Kc is constant at a set temperature. If you muck with the temperature, if you change the temperature, you're going to get a different Kc value, okay? So if you do something to the, like if you take a bunch of chlorine out and it then reaches equilibrium again, as long as you haven't changed the temperature, you can use that Kc value to work out whatever's missing. Because what you can do is if you need to determine, say for example at equilibrium you're able to figure out the concentrations of all of these, and you can make that the subject of the equation and work it out based on the Kc value. So there's some rearrangement involved here. Now we're given the information. Initially there's 1.0 moles of HCl and 0.25 moles of oxygen, and then we've got to change, and it's going to be 0.5 moles. Now how do you go from 1 to 0.5? Sorry? How much do you need to take away? Yeah, that's right. So we put in here negative 0.5. So it's dropped by half a mole. Now over here, 0.25, that's combined with that to make that. So is this going to be negative or positive, do you reckon? If that one's negative, if it's dropped, what's going to happen to this one? Some of that's gone away, and if some of that's going away, is some of that going to go with it? Yes, because they're both reagents. So if that's dropped by 0.5, what's the molar ratio between hydrochloric acid to oxygen? 4:1. So then, what's the change in oxygen going to be?
Negative 0.125.
Good. Listen, you can use a calculator for this. Sorry? Yeah. I mean, I did the 1 half over half thing in my head, because I saw that was a 4:1. So if that drops by 1 mole, or if we drop 4 moles on there, how many moles are going to drop here? 1. So if we drop a half a mole, then it's going to be a quarter of that. And it was done in the head, which is great. Okay, so what's 0.25 take 0.125? Yeah. You can see that they've initially engineered this problem to have nice round figures. Okay. Now we're assuming that there's none of this and none of this. I'm not aware of any of that being present. So the demonstrator mixed HCl and oxygen in a 5-litre vessel. So at the start, there was no water and no chlorine. It's not written in there, but that's something you need to just pick up from the way the question's written. So we start off by putting 0 and 0. It'll be unsurprising to you that we're going to have a plus figure in these two, simply because there was none there, and then some of this went, because it's negative, and that's made that. So you've got to use the molar ratios here. Now, what's the molar ratio between HCl and H2O?
1 to 2.
Yeah, 1:2. So how much is this going to change by?
Half of that, 0.2.
How about chlorine? Yeah, same. Alright, so in the end, yeah, because 0 plus 0.25 is 0.25. Now this isn't a 5-litre vessel. C equals N on V. So in order to get the final concentration for all of them, I'm going to need to divide them all by 5.
3.1.
Yeah, it is in 0.1.
0.025.
Really?
Yeah.
Just do it in your head.
It's only a quarter of that.
Oh, yeah, okay, I'll say it then.
And 0.5.
How much?
0.05.
Now remember that the figures here are in moles, the figures here are in moles, and the figures here are in moles. But now that we've used volume, this is going to be in moles per litre. Okay? Initial change in concentration. That's an ice table. Do this kind of ice and you'll just get better marks and a better razor. I think I got one laugh. Thank you. And
No problem.
yeah, make sure you click like on that motor there, everything I put up there. It makes me happy. Now the next question is, calculate the equilibrium constant for this reaction. Alright, so we need to do that. So we need to calculate the equilibrium constant, and we've got to do products over reactants. So it's going to be Kc will equal 0.05 squared times 0.05 squared, because we've done the chlorine and the water and their final concentrations, and we have to square them because of the molar coefficients. And that's going to be over 0.1 to the power of 4 times 0.025, and that's not times anything. So we end up with the Kc value, whatever it is, 0.05 squared times 0.05 squared divide 0.1 to the power cubed. Where's the power of that? Okay. Has anyone worked it out, or is it just me?
6. Infinite.
I got
1.4.
I got 2.5.
Same side.
And hopefully that's correct.
You could just half five and do 2.5.
Yeah, 2.5. So, based on this, what side is the reaction going to sit across to? Is it greater than 1 or less than 1?
Greater.
Okay, so what's it going to favour? And so it's going to favour going to the right. And that's exactly what's occurred. Now the next question is, state the equilibrium constant for the reaction below if it were conducted under identical conditions. And they've reversed the reaction. Well, you're going to do that. Flip. Yeah, well, products over reactants. So if we reverse this reaction, which is in the book, they've simply got it and switched it.
Negative.
No, it won't be negative. So it's going to be 0.1 by 0.025 divide 0.05 squared divide 0.05 squared 0.4. So if I flip that equation, it's 0.4. Now is that greater than or less than 1? Yeah, so which sides are going to favour? Not the ones what is written up there. It's going to favour the left-hand side, which is in line with what's already occurring. Now if you were to change the temperature, you'd change the Kc value there. But under any conditions, you wouldn't necessarily, or under the same conditions, you wouldn't necessarily need to have the, if it says it's at equilibrium, and you've got 3 of them, and it says what's the final concentration of something, you can just rearrange the equation given the Kc value and make that the subject of the equation. Just bearing in mind that you need to account for any molar coefficients that are present, okay? So if they start putting 4s and 5s and stuff in there, that can be an issue because I got a cubic root on here, and I got a square root. I don't know anything else. There must be a way to do it on the maths calculator, I'm not sure. Right, how's that? I know it's all very new, but it's a literal bouncing ball process.